Hmm? Okay. So, hello everyone. I'm going to talk about complexity theory, asymptotic analysis, just to get to know a little bit better how we usually, as computer science mostly, analyze algorithms. First, we are going to talk about this asymptotic analysis thing, and then we'll move to complexity theory and complexity classes. So first, I want to introduce you briefly the idea of the Bachmann-Landau notation. Probably you're familiar with it, but we have three different families of notations mainly, which are the big O, the big omega, and the big theta. You probably are familiar with this one, which is the one you usually take for to calculate complexities, and basically it's telling you what's the time complexity of the computation of an algorithm. We also have omega, which you can consider to be, like a lower bound or a best case scenario time analysis, and also the theta one, which we usually call the tight bound, which is basically telling you, okay, this method for sure is going to be matching this time complexity. So as I told you, we are measuring complexity and analyzing the cost of something. So we are mostly interested in time complexity and number of operations. For that, we are going to use this family of notations, but I'm going to define them more formally so that you know how to operate with them also. For big O, what we usually do is, well, I'm going to define first the big theta. Okay, as I told you, this is the what we call tight bound. What do we mean by that? Is that if you have a function f, let's have f of n, fx, this is going to be tightly bounded by another function gx, where this gx is, let's going to characterize this function as a function that is going to be asymptotically positive, meaning that if we take huge instances of the value of gx, the function is going to be always positive in the infinity. Then this function fx belongs to this tight bound of gx if and only if S6 constants, C1 and C2, and then another one, n, which are positive. And we know that we can bound fx this way. Okay? So we can tightly bound the function fx using gx, and that's what we meant by this notation. This is the exact bounded of the function. If you take a look at this, there is a lower bound and upper bound, and we restrict to this case, we get the omega definition, which is basically saying that we have a lower bound on the value of the function, and if you restrict to this one, you get the upper bound. So if you can use both definitions and say, for example, that if you know that fx is on the exact bound of gx, that means that fx is on the lower bound of gx, and fx is also in the lower bound. When we say lower bound, we refer to the best case scenario. So at least in the best case, we can do it in this, using this amount of computations. We usually refer to this one as the worst case scenario because it is the upper bound. Okay, so using this knowledge, we can start calculating some things. So for example, if I have something like this, what is the bound for this? It's going to be On. And how do I know that? Because I can bound it, I can upper bound this easily, let's say by a big constant and then n. And also, in particular, I can lower bound it. So this is going to be in the exact bound of the linear class. Okay, this is not something shocking, but sometimes you are facing more interesting algorithms, not just loops, which are mainly defined by what I just showed you, but sometimes you have something recursive. I'm going to talk about now a very famous algorithm in computer science, which is binary search. I don't know if you know about it, but it's really simple. Basically, you have a sorted, this is an array. It's going to be sorted, meaning that the values are sorted incrementally, and then we want to find in this array a target value. Let's call it t, and we want to know the position of t, of the element t, in the array. So how do you do this? You can iterate over the array, and then that means checking every single value until you get the t. That means that we are doing one operation for each case. That is going to be linear indeed. Not in the worst case scenario, but upperly bounded by the linear function, meaning the size of the whole array. But we can do it better because we know the array is already sorted. So what we do normally in computer science is we take the array, we check, we put a pointer at the end, a pointer at the beginning, the lower and the upper pointed. And what we do is we check the middle element. How do we know what the middle element is? We take this one to ensure that we have one. So we take this element, which is the one that is less or equal than the middle element, and then we check if that is the value we're looking for. If it is the value, we are done. If it is not, then if the value is lower, we are going to search here. If the value is greater, we are going to search here. So we change the pointer, and then the new pointer is here if we are looking for values over here, or we update the lower pointer with the values here. Okay, so if we try to analyze this, this is not as easy as the previous case because we have a recursive function, and what we have is something like this. So we are calling the binary search function. Let's go to compute the cost. So for each value n, what we are doing is basically trying to, we are calling the function again for the subpart, for the two different subproblems we are creating. So we have the cost of solving the subproblem, and we are only creating one subproblem because whether you are going to this side or this side, you are going just to one. But you have also the cost of computing the middle element and checking which side are you joining. Okay, so this is a constant value. So we have that, this is our recursive function. Okay, so what do we do here? This is not as easy to manage as the previous definition of the summatory. So in computer science, we have something really, really cool. I think you might find it useful, which is called the master theorem. This was a really, really, really good idea from 3 computer scientists in the late 80s, I think. So they came up with this idea of there are a lot of problems in computer science that are recursive in this sense. We have a function that is calling again that function to solve smaller instances of the same problem. And they come up with this idea that if you have a function, let's call t of n, that is going to be this is going to be monotonically increasing, meaning that it's not going to go down. The function is always going up in values, so it's always increasing. And then if the function satisfies the following, meaning that the function is going to be a recursive call, let's say, for example, for 1, and the rest of values are going to be something like this. Okay, so if the function can be expressed this way, which is basically a recursive call, we are going to call the function tn, and then if the value is 1, we know that we can compute and solve that instance because it's a small instance of the problem, and the cost of solving is c, let's say. And then if we don't know how to solve it, we are going to call the function a times for a different instances, and we are going to solve n divided by b subsets of the problem. And then we have also a small cost that we need to add to take into consideration the computations we are doing while splitting up the problem and everything. So if we know that the function is of this form, which is actually ours, then there is the master theorems tells you how to get the complexity class. So this means that we can categorize mostly every recursive problem in computer science easily. Basically, what the master theorem tells you is that if this f of x belongs to the exact class of n to the power of d for some d greater or equal than 0, then you can compute the bounds for Tn this way. You know that the bound is going to be n to the power of d if the following holds. Then we will have also the same for the equal and for greater than. Basically, we have different bounds on the function depending on the values of the number of calls we are making, and the number of subproblems we are creating, and also the cost, obviously, of the function itself, the function that takes into consideration the creation of the smallest problem and the join of the solutions of the subproblems. So we end up with this, just for the sake of having all the cases covered. Okay, so now you don't have to worry ever again about any recursive problem thanks to this beautiful theorem. In our particular case, which was the binary search, we got the recursive relation, and now we can compute easily the cost, even the type bound for the function, which is, as you can probably calculate, we are doing this a equal to 1 and then b equal to 2. Our function, our d is, well, is 0. But so when that being here, right? So if you substitute the values, we know that this is going to be in n to the power of 0, that's 1, and then we have log n, which is what you will expect if you do the calculation by brute force, right? You can also try to compute how many calls you're making, which is something like this. In the worst case scenario, you're going to have of this case easily to compute. But again, if you use the master theorem, you don't have to do this calculation manually. You can just plug in the values and then check what the outcome is. This is something that is really useful for every recursive problem analysis. Okay, so that's the first part of the talk. Now we can move to more complex things, indeed complexity theory itself. Let me check. Okay. Can I? Okay. So now that you have like a brief overview of how do we compute the cost of different algorithms, maybe you're wondering how do we classify these algorithms? And for that we use complexity theory. Complexity theory is basically the field of mathematics that try to classify how hard a problem is. So we need to define what we mean by hard problems and not hard problems. We are going to start by defining the first class of problems, which is going to be P. And P is the group of problems that are solvable in polynomial time. And this is solvable. So for example, the binary search one is in P because you know that we can bound this easily. So it's at least it is in P. It's even better than P because it's a logarithm approach, but it's in P. Also, when we were trying to calculate the summatory of something, this is also in P. So we have a lot of problems that are living in the P complexity class, and one, after taking a look at the P complexity class, might wonder, are there any problems that are not inside the P class? Okay, and thinking about this idea, there are a lot of classes, there are a lot of problems that are not in P, but the next step is, so you can also talk, so there are a lot of ways to measure complexity. We are not just taking into consideration the time, but of course you can define what is called P space, which is another class, it's a superclass of P, which is the algorithms that are solvable using a polynomial cost in space, in the memory. But this is far beyond what I want to talk about today.
What I mean is that any problem increasing the resources
yeah. No. So P space is not the last complexity class. There are others that are not solvable in P space. That are not in P space. They are out of the P space class. There are other classes. There are other classes. So. Yeah. There are a lot. Yeah, you can have some trade-offs. You can change. You can improve. You can use more memory to reduce the computation time, and you can increase the computation times to reduce the memory. No. We are just considering now the computation time. We don't care about the memory usage. We just care about the computation time. This will overlap with a lot of other classes, for sure. Even with the classes you're talking about, the one which limits the space and the ones which don't limit the space, this will have some overlap with P. So there are a bunch of classes. This is just one category we just defined. There are a lot of others, and there are a lot of overlap between the classes. Indeed, the whole study of these classes is called sometimes the complexity theory zoo, because there are like a bunch of them. So researchers are always defining new ones. It's really difficult to keep track of all of the different categories we currently have. But yeah, now we are just taking into consideration the time, just the time. This will overlap with what you mentioned. Okay, and apart from this one, I also want to introduce another category which is really, really famous, which is NP. Sometimes NP is misunderstood. NP does not stand for non-polynomial. NP is non-deterministic polynomial algorithms. And And when we say that, this is hard to explain because you can reach out to the NP definition by two different approaches. You can take into consideration what we call Turing machines and non-deterministic Turing machines. Let's call this NP. So basically, when I'm saying that the problem is solvable in polynomial time, I'm saying that it is solvable in polynomial time using a Turing machine. I'm not going to dive deep into the idea of what a Turing machine is, but it's basically a device that can compute programs, and it is related intrinsically to what we currently use as a computer. So you can take that as my computer can do it or cannot do it. And a non-deterministic Turing machine is basically a Turing machine that instead of following the paradigm, the methodology used commonly by computers, which is I'm in this state and I have a certain state, and I know how to compute the next step. So we have a transition function, and the transition function tells you exactly for this state, there is just one next step that is going to be this one. And for the next one, the same. So it's a linear approach to changing the state of your computer. But for non-deterministic Turing machines, the things go a little bit crazy because for each state, you can define a set of different states that are the next step, which can help you to actually do some tricks to compute the problems better. And yeah, so instead of doing that definition of NP in terms of Turing machines, which I think it's not clear at all, I'm going to define NP with the equivalent definition, which is saying that NP problems are problems that can be verified in polynomial time. I'm going to talk to you about verification. So this is not just all problems. We are going to focus on what we call decision problems. So a decision problem is basically a problem which for every input you have an algorithm that will output yes or not or no. Okay? So basically you are the two feasible answers are yes or no. Those are the only ones. That's what a decision problem is basically. Okay, so NP stands for every problem that you can verify the answer in polynomial time. And that is different from P. Well, we don't know yet, but it's going to be different from P, almost for sure. But we don't know. This is something we don't know. This is the big NP equals P problem. We don't know if those two categories overlap or even if they are the same. It's likely that they are different. We don't know yet. But we know some problems that are living here. And we don't know if they live here. And those problems are hard to crack. Because we can easily prove that the problem is living in P, in NP, because you can have solutions and verify that the solution is indeed a solution easily. But you cannot find if it is an algorithm that will solve the problem efficiently. Efficiently meaning polynomically in time. So the whole NP to P equals P questions is basically saying, it is as hard to prove that something is a solution as solving the problem itself. So that's it. That's what NP equals P is questioning. It's just that. It's the question of verifying a solution is the same as solving the problem. And sometimes it is. And sometimes it is, for sure. We know that, and it is easily to prove, that if this is the NP class, category, P is living there. That's for sure. Because if you know how to verify a solution, if you know how to solve a solution in polynomial time, you know how to verify the solution in polynomial time. I mean, just solve the problem. So we know this structure is there for sure. which what we don't know is whether or not there is something else or everything will collapse to just one category. Okay, any questions regarding this? So, there are some problems that are easy to prove that they are in NP. We are going to work with some of them. So there is this problem I really like. I think it's really simple to get the idea of why NP is here and probably is different to P. Most researchers think that way, but if you find a way to prove that NP and P are equal, you are solving a bunch of problems. And we will talk later about that. But now, let's focus on this. Let's focus on this first problem. Imagine that we are given a set of integers, and then we want to find a subset of this set that will verify the following property. So we have a set of integers, and we want to verify if there exists a subset of our original set that if we try to add all the numbers from that set, we get 0. Okay? So if you try to search, imagine if I tell you, okay, I know that there is a set, and let's call this S star, and S star is a solution. If I tell you that, you can easily verify that S star is a solution or not, right? You just take all the numbers, imagine that they can be listed, and there are n of them, then you will just take the sum and verify if they are equal to 0 or not. And how many operations I'm doing here? I'm doing n operations, so you can verify that the solution is indeed a solution, or the proposed solution is indeed a correct solution, and you can verify that in polynomial time, right? So this problem is living in P, in NP. Right? But is it living in P? That's a difficult question. If you know the answer, please tell me. But what we know for sure is that if you try a naive approach, a brute force approach, how would you do it? Okay, so one way to do this is considering all of the subsets of the S set, and then this means computing 2 to the n subsets, because whether or not you are in, let's just briefly detail this. So whether or not you are including an element, for each element we have x1, x2, we have all elements, and I can include it or no include it. So I have 2 options for each one. I can take this or I cannot take it. So what I'm doing here is basically saying I'm taking x2 or I'm not taking x2. And this means that I'm doing 2 times 2 times 2 different decisions. This adds up to 2 to the n. Okay? And then if we have to verify that the sum of each subset is equal to 0 or not, we need to do this linearly. So if you try a naive approach, you will end up with something like that. 2 to the n times n, which is not good. No one has yet found any solution to this problem efficiently. There is no known polynomial algorithm to solve this problem. And this leads to most of the researchers thinking, okay, there is something in NP that is hard. And because of that, we are going to talk about another concept on NP that is hardness. So apparently, one could think that all NP problems are the same, and we don't know yet. But by looking at the problems, we can define 2 different categories. which are related to NP. And those are NP hardness, NP hard problems, and NP complete problems. So what's an NP problem? An NP hard problem. So we know that our current classification of classes is following this structure. We have P, and we don't know if NP is going to be different to P, but let's assume it is. So we will have something like this. If both are the same, we just have one big circle. But imagine that they are different. What's NP? NP are some problems that are going to be living here. Are going to be living here. So this is NP. Those are NP problems, NP hard problems. As you can see, there is an overlap with NP. Again, this is assuming NP is different to NP, because otherwise this will be P also. But again, let's assume that they are different. NP hard problems are living there. And then we have this overlap, which is what we are going to call NP complete. So NP hard problems are living here for sure, and there are problems that are living here and are not in P. A problem that is not NP. That is NP. Oh, for example, okay, let's talk about one example. So there is this beautiful construction in mathematics related to what is called the Berry paradox. I don't know if you have heard about this, the Berry paradox. I think I wrote it. Yeah, so the Berry paradox is basically a paradox of mathematics that tells you that you cannot do something that is self-referring to itself. It's self-referring, because you end up having a lot of issues. I'm going to write down this sentence. Let's go to define the smallest positive integer not definable in under 60 letters. So that's a statement. We know that there are infinitely many positive integers. We know that the alphabet is limited to letters, so that number should exist for sure. Well, it must exist. But again, if this number exists, this means that we have just defined it with less than 60 letters, which is the sentence itself. So we end up with this paradox. I don't know if you knew this paradox, but it's the base of the problem we are going to talk about. It's the same idea. So it's basically something that is talking about itself. It's defining its own property. So it cannot be. Well, it ends up with a contradiction if you try to make sense out of this. So this is really common in mathematics, and it is used to prove something that it cannot be because it is self-referring. So instead of the Berry paradox, we're going to talk about something that is really similar, and it's probably one of the most famous problems in computer science, which is the halting problem. And it's basically the same idea as the Berry paradox, but this is, for example, an NP hard problem, okay? This is a problem living in NP. And it is not living in, it's an NP hard problem, but it's not an NP problem, okay? So the halting problem is basically this idea of how do we know as computer scientists whether or not given an arbitrary input, an arbitrary computer program, if the computer program will end or if will loop forever. We don't know. You can have a lot of different inputs, a lot of different programs, but if you had this beautiful program that could tell you, okay, I know for sure for this input and for this program, the program will end successfully or it will halt. So that's a halting problem. Okay, so basically, imagine that we know there is a solution for the halting problem, and we can do the same trick that we did for the very paradox. Let's call this beautiful function hold, and hold of f is equal to yes or no, whether the program stops. It doesn't. So if the program stops, the output of hold is yes, and if the program does not stop, the output of the program is no. Okay, let's imagine that the function is defined for every program. So the function is complete, is total. And let's imagine that we can define the function. If we could define this function, then we can do some tricks. Let's say, let's define this as if hold of g, then loop forever. So what happens now? If g loops forever, then this should not be executed, then it will not loop. But if it loops, well, sorry, I have to. Okay, so we just do the same trick that we did for the very paradox. That is defining something that is self-referring. So you cannot decide whether or not there is a solution. This is called also an undecidable problem. So problems that are not decidable by a Turing machine. And this is living here in NP-hard. So that's an example of a problem that is quite hard. Indeed, it's an NP-hard problem. And it's not living in NP, not living in P. Okay? So just so that you know some great examples of problems. Okay, going back to our classification, we have NP-hard and NP complete.
One of the things that, so because it looks very artificial, but actually, so artificial is one of the advantages of quantum complexity, is something that maybe we are missing when we are studying that, so that because you go to a problem, you can make problems equivalent, and then if you prove that the perfect problem is equivalent to another one, and this one is proved or undecidable, you're proving that this problem is also undecidable.
Yeah.
And this is something that is really interesting, because sometimes the problem is not so easy
Mm-hmm.
to prove that it's undecidable.
Yeah, yeah.
You can manage to ignore anything automatically. An example is a bit
Yeah, yeah.
deciding if dimensional Hamiltonian is that or not. This is undecidable because the map is close to the tapping pole, and then it means that if you have a dimensional Hamiltonian, you cannot prove, or any Turing machine can prove whether this is that or not.
Yeah, and that's linked to the next idea I wanted to talk about, which is actually, so we discussed about NP, we discussed about NP-hard problems, and we end up with this class that overlaps between NP and NP-hard. And you should be wondering, what the hell is this? So this is the class of all NP complete problems. What does it mean to be an NP problem, an NP complete problem? It means that you're in NP and you're also in NP-hard. But we haven't defined yet what an NP-hard problem is. I just told you that there is a problem called the halting problem that is living here and it's not living here. But what is this? So NP-hardness can be defined as every problem. Let's go into NP-hard problems are the set of problems well, let's define it another way. So let's call this a problem P, and P belongs to the NP-hard class if and only if this problem P, for every other problem living in NP, we can reduce P to C prime. And now we end up with this idea of reducing, which is what Mikkel was telling you about undecidable problems. And it is something that we do oftenly when you try to categorize things. So reducing a problem means that you're going to express the input of your first problem as the input of the other. And then if you know how to solve the second problem, you're solving the first one, right? So
In that case, if the definition depends that one that you can have, can give the problem from MP to NPR.
yeah.
How does it define itself the problems that are in NPR that are not in MP?
Or
So the problems that are in NPR that are not in MP, it means that there is not a symmetric reduction because
yeah, there is a one reduction.
that one.
So if a problem is in NP-hard, it means that if you solve the NP-hard problem, which you are not going to, but if you solve the NP-hard somehow, efficiently, then every NP problem will be solvable by using the same strategy. But we know there are some problems here that are not living here. Okay, so for NP-hard means that if you know how to solve a problem here in NP-hard, then you know how to solve every other problem in NP, because you can map the input from NP from the NP problem to the NP-hard problem instance, and then solve it using the strategy you know for NP-hard. Right? So that's what NP-hard means. So NP-hard is, this problem is at least as hard as any NP problem. For the problems that are living outside of the NP overlap, those problems are for sure hardest. For the overlap, we don't know. Right? Yes, sir. Okay, so how do we reduce something? I'm going to put the more formal definition here. But basically, you have two instances of two problems, A and B, and a family of functions, F. And these functions are going from the input of A to the input of B, the input of B. This is for F in the family of function. We have a family of function, then each function from the family maps the input of A to the input of B. If we know that these functions, this family of function is closed under composition, we also know that for every input in A exists a function that can do the following. Then we are reducing the problem A to the problem B. And that means that A is reduced under the family of function F to B. What we normally do is use family functions that are polynomically or that are polynomials or something like that. Then you can reduce a problem this way using different strategies. And that's how you categorize problems. For example, in this case, in the NP complete class, what we normally do is you take another NP complete problem, and if you know that this problem is NP complete, if you reduce your problem, if you reduce that problem to your problem, then you know that your problem is also an NP complete problem. Okay? So that's this idea of reducing problems from one to another. Probably you're wondering, okay, this is really nice if you already have some NP hard problems, because you can reduce your NP, you can use that NP hard problem to get new NP hard problems, but how was the first NP hard problem calculated? I'm not going to do it, I'm not going to compute it, because as you probably wonder, as you probably have noticed, proving that everything living in NP can be reduced to U, that's really hard. So there was a really nice guy, Cook, and he proved a theorem. I think it was the 60s, and this theorem is basically saying that the 3-sat problem is NP hard. So he proved it, and the rest of the people, well, now people are coming with another different approaches, but the idea is that you reuse what we already have. We already know a lot of NP hard problems, so we reuse them to do reductions. But the first one was this one, which is the satisfactorily problem. Just to briefly introduce it, it's basically this idea of if you are given a formula, a Boolean formula, for example, like this. You're given an arbitrary formula, a Boolean formula, and then you wonder, is there any assignment for all the variables that will turn out to be true? And this is an NP hard problem, so we don't know. We don't even know any efficient strategy to do it. Okay? Let's see. Okay. And there is one last thing I wanted to mention too, which is related to this idea of, well, keep in mind this is the whole diagram if we had P different to, so this is assuming P is not equal to NP, which we don't know, but if both classes collapses, then we will have this. Right? So this is really unlikely because we know that those guys are really, really hard to tackle. If you try to prove that P is different or equal to NP, you can try to tackle it using these problems. Basically, if you prove that an NP problem, an NP complete problem is in P, the whole diagram will collapse and you will end up with this one. But if you prove that something living here is never going to live here, we are also done. Okay? And again, this is not proving that something is polynomial or not. This is, the way I like to see this is that if P equals to NP, that means that verifying that's a solution, that something is a solution of a problem is the same as solving the problem. And if P is distinct to NP, it means that solving a problem is harder than knowing that something is a solution. I think that's a better way of phrase this idea. Okay, so one last thing. There are a lot of famous problems, and maybe you're wondering where are they living. There is this really famous problem, which you probably have worked with, which is the knapsack problem. Okay, so this is a problem that basically involves computing the max over a certain function. What we are doing is basically we have a knapsack and we are going to put some items inside the knapsack, and we know that each item has a certain value. So we want to maximize the value where xe is basically a binary value that tells you 1 if we take the item or 0 if we don't take it. So we want to maximize the value, but we are subject to a certain constraint, that is, we cannot take all of the items because we have a restriction on the maximum weight we can take. So this problem, as it is framed now, it means computing a set of, well, a tuple.
No, what is this?
subject to, well, subject to. So restricted to. Okay, so this problem, as it is framed, it means that we need to compute this tuple. And this is just a curiosity. If you have a problem like this, you could try to approach the problem in two different ways. You can ask, can I, how do you say this? You can ask whether or not there exists a solution that is, so you can ask whether or not there is an exact solution for this problem, or you can ask for the exact solution of the problem, so the optimal one. So those are two different questions, and the answer is different. It's the same as the problem of the travel salesman. You can wonder, is there any cycle that will, in any path that will solve the problem? Or you can wonder, what is the exact path that will solve the problem? Those two questions are different because one involves combinatory and the other don't. It doesn't. So just as a curiosity, one of them is living in NP complete and the other is out. The other is an NP hard problem, but it's even harder than the other. So this is just a reminder of whether or not you are verifying that something has a solution or whether or not you are checking for solutions is different to actually finding the solutions. This one? So this is interesting because if you try to solve it using a computer, we use something called dynamic programming. This leads us to another thing. So there are a lot of things going on with complexity because there are different ways of computing things and there are a lot of things to compute. But if you try to solve this using a computer and you want the exact solution, we will use something called dynamic programming, which basically is an approach that will compute every solution efficiently and then take the best one. How do we do this? We build a beautiful table with the maximum weight, and then here, no weight, and then we are going to pick the different items, and then depending on the different items, you get a different weight, and then you compute this table, and you can compute from here, look up for the maximum. So if one takes a look at this table, you might think, okay, we have n items, we have w weight, this is the cost. So that's not, that's a polynomial, right? But this is hiding how we are representing this number, and we are representing these numbers in digits. So indeed, this is something 2 to the power of t. So that's why, even though we are saying that this is a polynomial, it is not. And indeed, we call these pseudo-polynomial algorithms. Pseudo-polynomials because you are hiding something that is how you represent the data. In this case, we are representing decision numbers. So you are hiding it under a big complexity class. Complexity is a bit bound, let's say. But there are a lot of things like this. In this case, for example, if you know how to efficiently compute this, you could end up having this algorithm living living in P, which we don't know. We don't know if the exact problem is living in P. We will probably know. It will probably not be living in P, but we don't know. If you take the computation and you compute it this way, you can wrongly think that it's living in P, but it's not because it is hiding some constant. I think it's called pseudo polynomial. I have to check that. Any other question?
I don't know if it has been answered, but where does the problems that can be solved polynomically using a quantum computer enter in this?
So I'm not an expert at all in that. Um, Indeed, I think, Mikkel, do you know if I think BQP is living here. Is this under NP complete? I'm not sure. I have to look it up. No, it's not in NP. No. It's here. It's living here. So I'm not sure about quantum complexity classes because to compute BQP, we don't use a Turing machine. This is NP hard.
So there are no quantum computers cannot solve this NP hard.
We know that for sure? Yeah.
It's not exactly.
Okay, there are a lot of problems also with quantum complexity classes because, you know, this is not the same machine as we are using for P. It's not the same machine we are using for MP. For MP, we were using this non-deterministic Turing machine. For P, we use the deterministic one. For BQP, I think they use something called the quantum Turing machine, which is also the Merlin machine. Merlin? Merlin. I'm not an expert on that, but yeah. There are also some classes living here. So inside P, there are also more classes. We define them normally in computer science using different languages, and you have the regular languages over there, which is this. Probably if you have programmed something using regular expressions, you know this word, which is regex, and this is living here. And yeah, there are subcategories, of course, inside the P class, and there are even more categories outside NP and NP hard. And even if you consider, as Mikkel mentioned, as you consider space or other limitations on and constraints on the problem, then you have more classes, and this is a whole few of different complexity categories.
It seems like BQP also reaches some problems outside NP.
Here?
Contains B, part of NP, and part of
Oh. So there are a lot of things that we don't know yet for these classes. Yeah. So, yeah. The thing is that it is really hard to crack anything new on the field. Indeed, the complexity theory field is not a field with a lot of papers with breakthroughs every time. No, it's an old field with a lot of great results, but it is hard to come up with something new because of the difficult constraints on the problems and the difficult constraints on how you prove things. So. Yeah, and the other side even. There are other classes there. What? So depends on what are you questioning. Where 3SAT is an MP complete. It's MP complete. It's a decision problem. As far as I know. And yeah, any questions regarding these things? I don't know what times. I think so. I'm not an expert on combinatorial optimizations. Yeah, so if you are trying to compute the solutions, I think it is outside. If you are trying to address the decision problem linked to that, it's an NP complete. Most of the decision problems are living here. Okay.